Okay, maybe we can wait 1 more minute. I see people, I see people coming in. Okay. So Stefan, we may begin.
Okay, thank you very much, Yichun.
So it's our great pleasure to have Stefan Vaes to talk about the rigidity paradigms for embedding of 2-1 factors. Yes, welcome.
Thank you very much, Yichun, for the invitation, and thanks to all of you for setting up this global non-commutative geometry seminar. It's a very nice concept, so it's a pleasure to speak here and to give a talk on a recent paper that I've written together with Sorin Popa on rigidity for embeddings of 2-1 factors. And let me right away go into the subject. So as you all know, 2-1 factors, they arise in many different contexts, geometric, group theoretic, and so on. Groups, group actions, groupoids, all kind of different initial data. They give rise through canonical constructions to 2-1 factors. And in that context, there are actually two quite distinct paradigms that one studies. And the first one we label the many-to-one paradigm, where in often quite surprising ways, large classes of very distinct initial data may give rise to isomorphic 2-1 factors in surprising and often inexplicit ways. And then very much opposed to that, there is the rigidity paradigm, where in very different types of classes of initial data, it may happen that actually the 2-1 factor that you associate to this initial data completely remembers the data it was constructed from, and we get this kind of one-to-one Factorial constructions, if you wish. Now, of course, we have to say what one-to-one really means. It will always be in terms of one-to-one up to isomorphism. And in this talk, there will be obviously many different types of isomorphism that may arise. Of course, there is plain isomorphism of 2-1 factors. Very often there will be stable isomorphism of 2-1 factors. So 2-1 factors, they can be amplified by a positive real t. And when t is an integer, of course, you just take n by n matrices over the 2-1 factor. And in general, you pick a projection of the right trace in n by n matrices, and you take this corner. And in this way, you build an amplification, say t by t matrices, if you wish, t by t matrices over m. And stable isomorphism between n and m means that n is isomorphic with this t amplification of m for some positive t. Now, equally interesting is virtual isomorphism, which would amount to, roughly speaking, to saying that one is isomorphic to a finite index subfactor of the other. And there are many group theoretic and combinatorial situations where virtual isomorphism up to all kind of finite index and finite subgroup issues is the natural notion to look at. And then the weakest kind of isomorphism, which is, it's an equivalence relation, it's mutual embeddability. I mean, 1-to-1 factor can be embedded in the other and vice versa. Also, this is, of course, a kind of isomorphism relation. The prototype and very first many-to-one result is, of course, the famous one going all the way back to Murray and van Neumann, who introduced the definition of a hyperfinite 2-1 factor. So a 2-1 factor is hyperfinite if you can write it as the increasing union of finite dimensional subalgebras, so with the union being weakly dense. And the hyperfinite 2-1 factor R constructed, say, as an infinite tensor product of 2-by-2 matrices is, of course, the prototype example. And then the famous theorem of Murray and van Neumann says that all hyperfinite 2-1 factors are actually isomorphic. So here, for instance, I took 2-by-2 matrices and I repeated, but you could take any kind of finite size matrices and take infinite tensor products, whatever. Here you could still write explicit isomorphisms by tracing the proof of Murray and von Neumann, but still, I would say at that stage, it's a quite remarkable and surprising theorem that all hyperfinite 2-1 factors are isomorphic, with separable pre-dual, of course. And in the same vein, they proved that every 2-1 factor contains copies of the hyperfinite 2-1 factor, and many of them, really many of them. And they actually write a funny sentence in that paper in 43. They write that the possibility exists that any factor in the case 2-1, so that's the way they refer to a 2-1 factor. So the possibility exists that any 2-1 factor is isomorphic to a subring of any other such factor. So they don't exclude in their paper that actually mutual embeddability of 2-1 factors always holds. And remarkably, it took 25 years actually to prove that this is not the case. Probably it was not in these 25 years a main point of focus, but still it shows how subtle the concepts are. So let's fix some notation here with this kind of embedding arrow. I write n is embeddable in M if there exists a embedding of n into M. And now something funny happens. Somebody could write on my slide, and it was not me. So n is embeddable in M if there exists an embedding of n into M. And of course, in the world of 2-1 factors, any normal homomorphism is injective, and so that there is only one possible notion of embedding of 2-1 factors, of course. And when we decorate the symbol with an S, it means we pronounce this as stable embeddability. We say that n stably embeds in M if after taking an amplification, you can embed n into this amplified M. And that will be one of the main notions that we look at. Of course, after this work of Murray and von Neumann, the most famous many-to-one result still had to come, and was related to amenability. So it actually even persists here, this thing. I don't know who has put it there and whether it would be possible to remove it again, but it's funny. Anyway. So the most famous many-to-one result I will explain here is of course Alain Cohn's. And oh, thank you. But let me first introduce the concept of amenability, because this will already refute the statement on the previous slide of Murray and von Neumann that everything embeds into everything else. So as you know, a discrete group G is called amenable if there is an invariant mean on the group. So this means that there is a finitely additive probability M on the subsets of the group that is translation invariant in this way. So that's a concept also due to von Neumann, actually. And it's a concept that can also be defined more abstractly on the level of von Neumann algebras. So one can actually make sense of the notion of an invariant mean of a von Neumann algebra. So what is the good concept? If M is a von Neumann algebra sitting in B of H, then an invariant mean is nothing else than a conditional expectation, typically non-normal, of B of H back onto M. And one then proves that if you make a group von Neumann algebra, so a group 2-1 factor of an ICC group, is amenable in this abstract sense, if and only if G is an amenable group. And secondly, because that notion, of course, passes to subfactors, if M is an amenable 2-1 factor and N stably embeds into M, then necessarily N inherits the amenability. So amenability is a property that is inherited by subalgebras, and therefore, once these abstract concepts were introduced in the 1960s, an immediate consequence is that if lambda is a non-amenable group and gamma is an amenable group, it's impossible, there is no room to embed L of lambda, the group von Neumann algebra of lambda, into the one of gamma, not even after amplification. And secondly, and quite famously, there is Alain Cohn's theorem from 76, saying that this is the most general many-to-one result, that all amenable to one factors are isomorphic. So they are all hyperfinite and all isomorphic to the hyperfinite to one factor of Murray and von Neumann. So in particular, for all amenable groups with infinite conjugacy classes, L of G is isomorphic to R. And secondly, any to one factor that stably embeds into R inherits embeddability and must thus be R. So for this pre-order relation of embeddability or stable embeddability, really R is, say, the unique minimum, the minimal object in for this pre-order. Non-embeddability results, I mean, here there was the very first one, are typically quite hard to get. I mean, if I give you kind of randomly 2-to-1 factors to decide whether one can be embedded into the other is usually it's impossible to answer that type of question. But there are other qualitative properties that can do this. So Alain Cohn and von Jones, they gave a definition of Kazhdan's property T for 2-to-1 factors. And one consequence, for instance, is that if lambda is a group with Kazhdan's property T, while gamma is a group with the Hoyoroop property, there is no room to embed L of lambda into L of gamma. And if you don't know these notions of property T and the Hoyoroop property, here is a concrete instance of it. The group factor of SL3Z cannot be stably embedded in the one of a free group because of this reasoning. In the same spirit, there is a very beautiful result and work of Cowling and Hoyoroop 5 years later, saying that if you take a lattice in SP1n, this hyperbolic group, then if gamma n is such a lattice, if n is larger than m, it's impossible to embed L of gamma n into L of gamma m, even after amplification. And the reason is that there is a numerical constant for 2-to-1 factors. Nowadays, we call it the Cowling-Hoyoroop constant. The Cowling-Hoyoroop constant can be computed for these ones in terms of n, and it decreases if you go to subfactors. So therefore, there is this non-embeddability result. Both of these, and actually also the amenable versus non-amenable one on the previous slide, they are all, like, I would say, qualitative results, where there is the general phenomenon that more rigid objects cannot be embedded in less rigid objects. But in a way, these are not like very precise results. It's like really based on properties, that things with certain properties cannot be embedded in things with less rigid properties. Okay, let me complete this picture before moving to our work by stating a few other quite beautiful results. For instance, when you look at isomorphism of group von Neumann algebras of property T groups, of course, it's wide open whether the arrow that sends a group to its group von Neumann algebra is 1-to-1 on ICC property T groups. So this is sometimes referred to as Cohn's rigidity conjecture. I think it's safe to make this conjecture, say, for lattices in higher rank simple Lie groups, that indeed it's safe to conjecture that the arrow is 1-to-1. For these wild ICC hyperbolic property T groups, I mean, who can be like, I mean, this is a world on its own. I would be very surprised that it would hold in such generality. But nevertheless, what Sorin Popa could prove is that the arrow is necessarily countable to 1. So that's already, it's an imprecise, but still a striking result. And secondly, Ozawa proved in a very kind of general statement that the world of 2-to-1 factors is very rich, because there is no separable 2-to-1 factor that has room for all others to embed into it. Yeah, there is no universal separable 2-to-1 factor. So this embedding relation that we are looking at in this talk has no upper bound. So often I will leave out the word separable. So keep in mind that everything I say has separable in the back of its mind, because otherwise many things get strange statements. Here are a few conjectures and open problems. So I already mentioned the rigidity conjecture for lattices in higher rank simple Lie groups. I think it's even safe to conjecture that if n is larger than m, there is no room to embed the group von Neumann algebra of SLNZ in the one of SLM Z. But we really lack tools to even approach this problem at this stage. Equally intriguingly, I actually do believe that a von Neumann algebra version of the von Neumann-Day problem might be true. So what was the von Neumann-Day problem? It was asking whether every non-amenable group contains a copy of F2, of the free group with two generators. Nowadays, of course, we know that this is not true. There are like rather weird, non-amenable groups that do not contain free groups. But on the level of 2-1 factors, this might actually be true. And I actually believe that any non-amenable 2-1 factor should contain a copy of L of F2. And then in terms of, say, lower bounds for this pre-order relation, the next question you ask, and what can embed into L of F2? And also here, there are certain beliefs and conjectures to make that actually the only 2-1 factors that should be embeddable in L of F2 should actually be isomorphic to the so-called interpolated free group factors. But that again would require many new methods to approach this. Yeah. So all this to explain and show that this embedding relation or pre-order relation of embeddability is kind of subtle. Now, the problems that Sorin and I were looking at in the past months had to do with the following question. So how rich is this pre-order relation? For instance, can we have like chains of embeddable but non-isomorphic 2-1 factors? Can we have like huge families that are mutually non-embeddable, and so on and so forth? And we could solve these things based on a very generic construction that turns out to be extremely rigid. And it uses so-called left-right Bernoulli cross products. So here is the construction. You take a group like the free group. There is some liberty on the group to take, but let's take the free group. And take any amenable von Neumann algebra with a trace. And in a minute, we will take it two-dimensional, or you take 2x2 matrices. I mean, really something rather small, say. You take an infinite tensor product of it indexed by the group gamma. So you have this infinite tensor product. And then the usual Bernoulli shift would just shift this index set by left multiplication. But of course, we can also right shift. So I now do both the left and the right shift. And I make the cross product with gamma times gamma. And this is my 2-1 factor indexed by A0 with its trace. And the remarkable rigidity is that this construction is so rigid that the only way to embed one of these stably into another is in actually some kind of the obvious ways, because the base algebra can be embedded in a trace preserving way in the other base algebra. And of course, now you can build all kinds of things. Yeah. For instance, let's look at the easiest example, take 2x2 matrices. The trace on 2x2 matrices, of course, is just given by one parameter A between 0 and say 1/2 for the convention. And then, of course, you get that they are mutually non-embeddable. I mean, you have this one parameter family, and none of them embeds into any other of these. But you can play games. You can take a probability space that consists of an interval with length A with the Lebesgue measure, and then an atom with weight 1 minus A. So you see, if the A grows, there is an obvious embedding and there is no other. So you get a family of 2-1 factors such that MA, it's a one parameter family, MA can be stably embedded into MB, even only if A is smaller or equal B. So this is really a chain for this stable embedding or embedding pre-order relation. And a final nice example is you take as A0 two copies, a direct sum of two copies of the hyperfinite 2-1 factor. The trace on this is also again given by a parameter a between 0 and 1/2, because you have to say what is the weight here and what is the weight there. And then you vary this parameter, and what you get is a 1-parameter family of 2-1 factors. Each of them is embeddable into the other, but none of them is isomorphic, not even virtually isomorphic. So they can be embedded all into the others, but always necessarily with infinite index. Okay, just to illustrate what these things can tell you. So we will exploit this construction much further, but let me first illustrate this, how we can also use it to give examples of 2-1 factors with specified invariants. And let me first introduce this by looking at one of the more intriguing invariants, the fundamental group. A bit of an unfortunate terminology, but that's it. So the fundamental group of a 2-1 factor, it's a subgroup of the positive real line introduced by Murray and van Neumann, and it consists of the positive reals such that the T amplification of M is isomorphic with M. So what do we know about fundamental groups of 2-1 factors? Well, here is a very quick overview. Murray and van Neumann could only prove for certain 2-1 factors that the fundamental group was the entire R+. I mean, once you have the hyperfinite 2-1 factor or things that tensor with R, they have this fundamental group already by the work of Murray and van Neumann. Then Alain Kohn could prove that in the world of property T groups, where things are much more rigid, the fundamental group of L of gamma is necessarily countable. And quite recently, actually, there were a few concrete constructions of ICC property T groups for which this is a trivial fundamental group, but that's a very recent thing. All the time, it remained open to prove that there was a 2-1 factor with trivial fundamental group. For instance, it remained open all the time whether there was a 2-1 factor M that's not isomorphic to 2x2 matrices over M. And that was then ultimately solved by Sorin Popa. And that was really the start of his remarkable deformation rigidity theory for 2-1 factors, where Sorin proved that if you take the cross product of SL2Z acting by automorphisms of the 2 torus, then the cross product has trivial fundamental group. And the way he proved this is by really combining uniqueness results on this so-called Cartan subalgebra, combined with work on the fundamental group for equivalence relations, and that's mainly work of Damien Caborio. The construction was refined, although it was kind of a different construction than the one in the previous point, to realize any countable subgroup of R+, very explicitly, as fundamental group of a 2-1 factor. And then, quite a bit later, Sorin and I, we proved, still in the world of separable pre-dual, that there are really many uncountable, but necessarily Borel subgroups of R+ that can arise as fundamental group with explicit computations. And I will come back to that in a minute. And then finally, to complement the result here of 2001, Sorin and I, we proved very general uniqueness results on Cartan subalgebras, and as a consequence, for instance, whatever cross product you make with F2, or for that matter with SL2Z, and with many other types of groups, whatever cross product you make with F2, the fundamental group is always trivial. Now, what is really a wide open and from the descriptive set theory, I think, point of view, interesting question is to really describe what are possible fundamental groups of 2-1 factors with separable pre-dual. I mean, this is really a descriptive set theory question now, I would say. We know that they must be Borel sets, and we also know that as a group, they are so-called polishable. So there is a Polish group structure on it. Of course, not the one inherited from R+, I mean, a much stricter one. But I mean, there is still a huge gap between what we can construct and the descriptive set theoretically extremely wild world of Borel subgroups of R+. I mean, there are really in the Borel hierarchy, at every stage of the hierarchy, there are subgroups of R. Yeah, I mean, it's kind of a weird world. Anyway, I don't want to go much further into fundamental groups, but I want to turn to a variant on which we could get new results, where actually we look at embeddings. So the so-called one-sided fundamental group, so that's a notion that Adrian Ioana introduced, and which in a minute I will relate to, of course, cons correspondences and bimodules. So what's the one-sided fundamental group? You wonder now, given a 2-1 factor, for which positive t can I embed m in mt? Obviously, I can embed m diagonally in n by n matrices. So always the natural numbers sit inside. And let's, for brevity, denote with f this subset of the positive real line for a given fixed 2-1 factor. I can compose 2 embeddings, and therefore f is closed under multiplication. But now I have extra liberty. I can take the direct sum of 2 embeddings. So f is closed under addition. If I can also take infinite direct sums. So once f intersects with the interval 0, 1, then by composition, I can get arbitrarily small numbers in f. And with infinite direct sums, I can thus make everything. Okay, these are obvious restrictions. Now, actually, the only known computations where you can really determine for a given 2-1 factor how this looks like, it's either the minimal thing or everything. And quite remarkably, playing with the 2-1 factors that I gave by these left-right Bernoulli actions, on the countable level, we can produce anything. So if I give you a countable subset, of course, we should not intersect 0, 1, because that's not interesting for that reason. So I take a countable subset of 1 plus infinity, containing the naturals. That's essential because of this. Closed under addition, closed under multiplication. Then here is a concrete construction of such a 2-1 factor with one-sided fundamental group F. We take one of these left-right Bernoulli cross products to the power 1 over S, free product indexed by F. And the one-sided fundamental group is precisely F. So for instance, you could do this with F equal n plus square root p of n, or whatever game you want to play with these kind of semi-rings that live inside the positive reals. Okay, so that's one application of our methods that I wanted to show. Here is another application. So I will actually give you a functor from groups to ICC groups. We called it an augmentation functor. And to any infinite group gamma, I will, in a factorial way, associate a new ICC group H gamma. And let me already show you the conclusion. That functor will be like really functorial in the sense that lambda as a group embeds in gamma, even only if this 2-1 factor, this group von Neumann algebra, stably embeds into this group von Neumann algebra. So what is the consequence already here? That the world of which 2-1 factors can embed in which other 2-1 factors is at least as complicated as which groups can embed in which groups. So this means that it's wild, yeah? And the remarkable thing is that this is a very concrete construction. Of course, the construction that I will show you will not be really illuminating, but it's not like a matter of choice or whatever. It's a canonical functorial Bernoulli type construction, but it looks daunting. So here is the functorial construction. I start with an infinite group. I take a free group with many generators, namely a dummy generator A0, and then for each group element, a generator. Of course, I now have a canonical surjective homomorphism from G gamma to the free product of Z and gamma, where the dummy generator goes to the generator of Z, and each AG generator goes to the group element G. Yeah? So this is kind of like, how to say, factorial construction to write your group as a quotient of a free group. Yeah. And now I take n gamma, a subgroup of G gamma, namely the inverse image of gamma. I take the direct sum of 2 copies of G gamma, and I embed G gamma can be embedded diagonally, but I take only the image of n gamma diagonally. I build this countable set on which the group acts. I have this kind of read product, permutational read product, whatever semi-direct product construction. It's extremely ad hoc, I agree, but it's explicit and functorial, and it has this remarkable property. So of course, since embeddability of groups is wild, this means that embeddability of 2-1 factors is equally wild. And here are the conclusions. So on one of the earlier slides, I already showed you that we have this 1 parameter family of 2-1 factors where you have embeddability even only if t is smaller or equal r. Now, actually, with the construction on the previous slide, you can do that now with any partially ordered set. And here are the separability notions. If I want to stay within the world of separable 2-1 factors, of course, there cannot be like, there must be some kind of cardinality bound on I. I mean, you cannot do just anything. So you can immediately forget about these 2 points. Let me just say that I want to introduce a notion of separability for a partially ordered set. So I will say that a subset is subdense if every element of I can be written as the supremum of a subset of I0. And then I say that a partially ordered set is separable if there exists a countable and in that way subdense subset. Of course, the reals is subdense in this obvious way. And here is then the theorem. Whenever you have a partial order that is separable in that way, there is a concrete and factorial construction of a family of separable 2-1 factors that reflects this partial order under the stable embedding relation. So Mi stably embeds in Mj, even only if I is smaller or equal j, even only if there is embedding. In specific cases, especially with chains, you can do slightly better than just separability. So for instance, also with the first uncountable ordinal, you can explicitly give a family of 2-1 factors indexed by the first uncountable ordinal in such a way that embeddability and stable embeddability is reflected by the inequality of ordinal numbers. And this is then, of course, a chain that in a very explicit way says that there is no universal separable 2-1 factor, because of course this chain is too long to sit in a supremum 2-1 factor that would be separable, yeah, in a very explicit way. Okay, let me turn to a connection with bimodules, where also there are a few results. So before turning to the picture of bimodules, let me view it, because I was talking all the time about embeddings, let me view it as embedding a 2-1 factor in an amplification of itself. So I will call stable self-embedding any embedding of M into an amplification of M. And we say that such an embedding is trivial if the D is an integer, and up to unitary conjugacy, I have just embedded diagonally M in D by D matrices over M. And what I want to look at is 2-1 factors for which all such embeddings must be trivial. So without any index consideration here. And this is, of course, I mean, these are extremely remarkable rigid objects, yeah, because they must have trivial fundamental group. Every automorphism must be inner. They cannot have non-trivial finite index subfactors. So these are, I mean, very rigid objects. And it was, of course, open whether this could happen. There was an unpublished result indicating that this should be possible. But now we have very explicit examples. So if you want to deal with cross products, you have to work with groups that have no finite dimensional unitary representations. So here is a canonical construction. You take the group of finite even permutations of n, so that's a locally finite group. You take its free product with itself, and I will not write a concrete formula, but we have a concrete and again generalized Bernoulli type action, such that this cross product one factor has no non-trivial self-embeddings, because we are in this world where we can completely describe any embedding of M in amplifications of M. Okay, so these are concrete constructions of 2-1 factors without stable self-embeddings, except the trivial ones. Now, this is very much connected to Kahn's correspondences, because of course, a self-embedding of M in MD is nothing else than a Hilbert bimodule. I mean, it's just a dictionary. It's a Hilbert bimodule that is of finite dimension as a right M module, say, because since it's of dimension D as a right module, it's actually M to the D, and then the left action creates this embedding, of course. So for instance, the previous slide was saying that for these extremely rigid 2-1 factors M, every M bimodule of finite right dimension is a multiple of the trivial M bimodule. Unitary conjugacy of embeddings is the same as isomorphism of bimodules. Obviously, composition of embeddings is the contents or product of bimodules. Direct sum of embeddings is the direct sum of bimodules anyway. And you get a semi-ring. I mean, you do this up to unitary conjugacy, up to isomorphism, and you get the semi-ring of Hilbert bimodules of finite dimension on one side. And examples where there are no non-trivial self-embeddings are those where this semi-ring is as small as possible, just the natural numbers. Now, not surprisingly, if I give you a random 2-1 factor, you have no tools at all to compute this. I mean, typically this is wild and huge. Yeah. Now, in specific cases, you can now compute it. And for instance, what we showed through these Factorial constructions is that for many semigroups, there is an explicit construction of a 2-1 factor M, such that this semi-ring of self-embeddings or of bimodules is just the semi-ring of formal positive linear combinations of elements of S. Yeah? If I give you a semi-group, then formal linear combinations form a semi-ring, and you can construct a 2-1 factor for which precisely this is the semi-ring of stable self-embeddings. Now, this brings me to the point where I will say scale down a little bit and say something about automorphisms, because this may not, if you have never worked with bimodules or subfactors, this may look as a bit of a weird thing to do. While automorphism groups, of course, are extremely natural to look at. This embedding semi-ring is a richer invariant. It encodes, in particular, the outer automorphism group of the 2-1 factor. So what is the outer automorphism group of a 2-1 factor? It's the group of all automorphisms divided by the normal subgroup of inner automorphisms. And we will say that the 2-1 factor is full if these inner automorphisms form a closed subgroup of the automorphism group. And then, of course, this outer automorphism group becomes a nice Polish group. It's still, let me first say this last point, a wide open problem to intrinsically characterize which Polish groups can arise as outer automorphism group of 2-1 factors. Now, the construction that Sorin and I now proposed provides such a lot of freedom that not only we can reproduce all known outer automorphism groups again, but also many new classes of Polish groups are now realized. For instance, any closed subgroup of the Polish group of permutations of a countable set is realized as an automorphism group of a 2-1 factor, an outer automorphism group of a 2-1 factor. And there really are of course, many closed subgroups of these permutations, because it's like any Polish group that is acting on some countable structure somewhere is like this, of course. Also, unitary groups of von Neumann algebras can be realized, locally compact, totally disconnected groups, all compact groups, of course, because of the previous thing, all countable groups, and so on and so forth. Okay, a final thing before giving a glimpse of the methods that we use is in specific cases, we can go one step further. So I was saying that we have these families of 2-1 factors that are indexed by a partially ordered set. And this means that Mi can be stably embedded in Mj, even only if I is smaller or equal j. Now, in certain cases, and in order theory, this is a well-known notion, we call this a complete interval if actually nothing can fit in between, in the sense that we call such a thing a complete interval if, moreover, if any 2-1 factor that sits in between, then it must already appear in the list. Yeah, I mean, there must be a k in my partially ordered set for which n is stably isomorphic with mk. So then you not only have this partially ordered family of 2-1 factors, but you didn't miss anything that can be up to embedding put in between. Well, actually, even that is realizable in many cases. So as you know, a partially ordered set is called a lattice if you can take supremum and infimum of any two elements. And for instance, any finite lattice can be realized as such a complete interval. So and this is quite remarkable. So you draw any finite lattice on a sheet of paper, you can produce a 2-1, you can put at any point a 2-1 factor, and not only they are like canonically embedded in the way prescribed by the lattice, but no other embeddings can exist and no other thing can be sneaked in between. And this can be pushed further to so-called separable, we have seen as a notion, algebraic lattices. Now, I will not go into the definitions of this, but this means that even quite a lot of infinite lattices with suprema and infima and a few other properties can be realized as such complete intervals of 2-1 factors. So for instance, here is of course just a silly example, an infinite one where you take z with plus infinity and minus infinity added in the obvious way. That's an algebraic lattice. And we have a construction of this family of 2-1 factors. And the only way they can be embedded is when there is the correct inequality on the level of the indices. But also if n is any 2-1 factor that sits in between m infinity and m plus infinity up to embeddability, I mean, not just in the canonical position, but up to any embedding, then it must be one of the MKs. Okay, so what can I say about the proofs? So let me say in say 7-8 minutes, what are the main techniques that we use? So actually, I said that we are working with these left-right Bernoulli actions. So let me introduce a little bit of extra notation and extra liberty. So we have this base algebra A0 with a trace and a group gamma. And we take an infinite tensor product indexed by gamma of this base algebra, and we call it A. Now, since this is an infinite tensor product, for every k in gamma, I have this coordinate embedding, say, where A0 sits inside the infinite tensor product in coordinate k. Now, what is the left-right Bernoulli action? It's the action that would send the coordinate in k, of course, to the coordinate in GKH inverse. And now comes the extra liberty. My extra liberty is, moreover, as initial data, an action of gamma on A0. And I plug that also into the construction. Of course, you could take the trivial action. Then you're back to my earlier slides on left-right Bernoulli. And I make this cross product. Now, these days in deformation rigidity theory, we know so much things when gamma is a free group, or actually a free product of amenable groups, or those who want to know, I mean, there is, of course, a kind of conceptual class of groups for which we know this kind of behavior. They are very much free-like, say. Hyperbolic groups would fit in the picture. They are so rigid that whenever you embed any of these structures into another up to amplification, after a unitary conjugacy, you can move around things thanks to Popper's deformation rigidity theory, so that they must map the group von Neumann algebra into the group von Neumann algebra. Okay, believe it or not, but that's what you can do thanks to Popper's theory. And moreover, and that is a conceptual thing that I want to present to you on the final slide, not only you can turn things so that group von Neumann algebra goes into group von Neumann algebra up to amplification, but there is a concept of height for embeddings of group von Neumann algebras, and that's a very conceptual thing that I will introduce. You get that the height of the embedding is positive, and from that point on, you can deduce that theta is essentially group-like on lambda times lambda. It's essentially embedding one group into the other group up to all kind of finite representation and finite whatever issues. And once, of course, you have unraveled things like that, it's like in chess, you know you have won, but you still have to play the end game that I will not go into. But this height thing, even if you're lost in all the notations, you can forget about everything, because that's extremely general. It's a very general thing on group von Neumann algebras, and it's a kind of harmonic analysis concept, if you wish. So when V is a unitary in a group von Neumann algebra, the height of the unitary is just the largest Fourier coefficient, the absolute value of the largest Fourier coefficient. So the max or the supremum, it's attained of all traces of V UG star. UG is the canonical unitary in L gamma. And then when I have a subgroup of unitaries, I define its height as the infimum of all these maximal Fourier coefficients. So now try to think what this means. If G is a subgroup of unitaries with positive height, so you know that these unitaries, they can, of course, say live on several group elements, but they still have to have certain concentrations on not too large subsets. Anyway, that's the notion of height. Now, that was an absolutely crucial notion in the paper that Adrian Joanna and Sorin Poppa and myself wrote on superrigidity for group von Neumann algebras. And the very general result that we proved for arbitrary groups with infinite conjugacy classes is that if you have an isomorphism, not embedding, an isomorphism of group von Neumann algebras, then really positive height for the embedding, because theta, of course, lambda is a subgroup of unitaries in L gamma. So theta of lambda is now unitaries here. If this group of unitaries has positive height with respect to gamma, that's really equivalent on the nose in full generality with the isomorphism being group-like, meaning that after a unitary conjugacy, which you always have to allow, the isomorphism becomes an isomorphism of the groups and a character of the group, which also you always have this liberty to define in that way an isomorphism. Yeah. Now, so this was at the heart of our superrigidity theorems back in 2010. Now, what is at the heart of our new paper earlier this year is to prove such a result, but it becomes more technical, not for isomorphisms, but for embeddings, and also allowing amplifications. Now, of course, then you have to cater for all kind of finite dimensional representation issues and finite index subgroups issues and so on and so forth. So I will not write the key technical theorem, but I did want to advertise this one because it's, I think, a very conceptual one. Why? The second bullet point, you can never hope to prove in a concrete case, but the first one you can hope to prove, because that's a kind of analytic thing. If you have a good context, you may hope to be able to prove from more abstract considerations that such a height is positive. Because if you refute it, it's very open to proofs by contradiction. If this does not hold, well, what you get is a sequence of group elements for which Fourier coefficients tend to 0. So you can hope that with that you can do things, and that's indeed how these proofs in deformation rigidity theory work. Okay, that's all I wanted to tell you. Thank you very much.
Hey, thank you, Stefan, for the beautiful talk. And I believe we should have some comments from the audience.
Okay.
Are there?
Yeah, I have one comment, because the construction that you described, I mean, it reminded me of what is called the Lamplighter group. I mean, yes, and so I mean, in a kind of a strange manner, we had on Friday we had a talk by Pereira about the Atiyah conjecture. I mean, which is in fact a problem posed by Atiyah, and I mean, in this problem, it's a problem where you want to determine the values, the possible values of the Betti numbers for the L2 index of coverings, but it can be reformulated as a purely algebraic problem for the group ring in relation with the corresponding 2-1 factor. Because what you want to do, you want to evaluate essentially the trace of the 2-1 factor on the kernels of operators which belong to the group ring inside the 2-1 factor. Now, what was very striking in the talk of Pereira was that, okay, so the situation is unknown in the case when the group is torsion-free, but typically for the Lamplighter group, where you have this Z2 many times, there, of course, you have many subgroups of finite index. And then what I was struck by in the talk was that somehow there are constructions, but there doesn't seem to be a good idea about a guess of what this set of possible values for the Betti numbers are. So if you want, there is still the conjecture that, for instance, for torsion-free, it is just the integers. On the other hand, it's exactly compatible with the inclusion, with the embeddings that you are talking about, because if you take a subgroup of a group, then there is an obvious inclusion of the values for one group into the other. So I am quite curious to see. I mean, if of course, with the many examples you had, I mean, it seems very clear that okay, one could give values for arbitrary ranges and so on and so forth. But I believe that the problem of exactly guessing what type of set one gets should be, sort of comparable to the type of results that you have. I mean. So I mean, what I am suggesting is really that you look a bit. I don't know if you did already, or you probably did. But
we actually did. So this is a very interesting point. I thought that there were some guesses, not more than guesses, that computable numbers would be the good guess, because they almost have this method, I thought, to, unless we are not thinking of the same notions, of encoding a Turing machine in such elements of
yes, no, you are perfectly right. But what I would like to have is the following. For instance, okay, Zook and his collaborators, they proved that 1/3 is a value for the Lamplighter group. Now, of course, 1/3 is the sum of positive powers of 1/4. So I mean, and of course, what I am asking is to try to find a general guess for arbitrary groups of involving, of course, the torsion subgroups of what the range could be. You see what I mean? It seems to me to be a problem of the same. Well, of course, it has an purely algebraic side because you restrict to the group ring. But apart from that, I mean, it seems to be of the same flavor. I mean, but sure. you did look already. I mean,
but that's an extremely hard problem, of course, to make such a guess in general. Yeah, definitely.
Yeah, I mean, And the other question which I have is about the rigidity conjecture. So, I mean, as you said, I mean, of course, it should be only in the case of lattices. But then my question is the following. What I am very curious about in this type of development is to find if the Furstenberg boundary as a concept can be adapted in the case of 2-1 factors.
It has now been adapted, actually.
It has now been adapted. Oh, wow,
Yes.
that's great. Yeah.
So there is a quite recent paper of Jesse Peterson and his former student, I think, or postdoc, Sayan Das, and there is a concept of Furstenberg boundary. Okay. And there are first consequences already, I think, but there is still a lot of payoff, I think, to expect. It's yeah, definitely.
Yeah, of course, yes. There should be because somehow, you know, what is also very striking is the fact that once one has some kind of conceptual construction of this type, it is not necessarily true that it is restricted to the problems that you started with. It can have applications in many other directions, just because, you know, it's a flexible concept and so on. And I mean, also what was underlying some of the proofs, like of the rigidity, I mean, you know, it's the concept of teeth building and so on, and the enormous rigidity that there is behind that. So, I mean, since, you know, you control 2-1 factors so well, I mean, one is wondering whether, you know, one can sort of extract from the 2-1 factor a combinatorial object, which has this type of extraordinary structure. I mean, what I retain from your talk is that, well, okay, I mean, there is an incredible world there. I mean, you know, which is so elaborate that okay, I mean, it's so. Can you sort of summarize in a few words? I mean, what is your mental picture now of the 2-1 factors? I mean,
that there are a few classes that are now that have a lot of structure and are completely understood how they can embed inside the other, how they can be isomorphic or not. But this is like a tiny subset of,
I see. Yes,
say, random 2-1 factors where you basically don't know anything.
I see what you mean. Yes.
Okay. Are there any other questions or comments? Okay. So let's thank Stefan again for the beautiful talk.
Great talk.
And,
yeah. Thank you very much.
And next week we will have Benoit Collins from Kyoto, and in 2 weeks, on April the 5th, there will be Omar Motion from Muse